Newton's first law of motion is called inertia. Inertia could be simply another name for mass. This lesson is very heavy on looking into the history of mechanics, mechanical physics. So we'll be talking about some of the early Greeks, Galileo, Newton, etc. Describe Aristotle's concept of motion. Describe Copernicus's idea about Earth's motion. Describe Galileo's idea about when a force is needed to keep an object moving. State Newton's first law of motion. Describe the relationship between mass and inertia. Explain how the law of inertia applies to objects in motion. The big idea: forces cause changes in motion. If you see a ball at rest in the middle of a flat field, you know it's in equilibrium. No net force acts on it. But if you suddenly saw it begin to move across the ground, you'd look for forces that don't balance to zero. If there's no wind and nobody kicking it, you might look to see if someone was pulling the ball with a rope or pushing it with a stick. You would reason that something was causing it to move. We don't believe that changes in motion occur without cause. Discover: can you snap a card out from under a coin? 1. Balance a half of a 3-inch by 5-inch file card on the tip of an index finger. Place a penny on the card just above your finger. Give the card a quick horizontal snap with your finger and your other index finger. Repeat steps 1 through 3 using a quarter. Analyze and conclude, observing what happened to the penny when the card was quickly removed. Did changing the coin affect results? Predicting: do you think this would work with a card made of sandpaper? Making generalizations: why were you able to snap the card without moving the coin? Aristotle on motion, 3.1. The idea that a force causes motion goes back to the 4th century BCE, when the Greeks were developing some of the ideas of science. Aristotle, the foremost Greek scientist, studied motion and divided it into 2 types: natural motion and violent motion. The sentences with the lightning bolt are worth noting, so pay special attention to those sentences. They will become very important. Natural motion on Earth was thought to be either straight up or straight down, such as a boulder falling towards the ground or a puff of smoke rising to the air. Objects would seek their natural resting place: boulders on the ground and smoke high in the air like the clouds. It was natural for heavy things to fall and for light things to rise. Aristotle proclaimed circular motion was natural for the heavens, for he saw both circular motion and the heavens as being without beginning or end. Aristotle, link to history. Aristotle was the most famous philosopher, scientist, and educator of ancient Greece. He was the son of a physician who personally served the king of Macedonia. At age 17, Aristotle entered the Academy of Plato, where he worked and studied for 20 years until Plato's death. He then became the tutor of young Alexander the Great. 8 years later, Aristotle formed his own school, and pictured here is Plato, Aristotle's teacher. His aim was to arrange existing knowledge in a system, just as Euclid had done earlier with geometry. And there's a picture of Euclid. Aristotle made careful observations, collected specimens, and gathered together and classified almost all existing knowledge of the physical world. His systematic approach became the method from which European science later arose. It is the mark of an educated mind to be able to entertain a thought without accepting it. Aristotle. There's a bust of Aristotle, and here's another bust of Aristotle, one of the ancient Greeks. After his death, his voluminous notebooks were preserved in caves near his home and were later sold to the Library of Alexandria. Scholarly activity came to a stop in most of Europe during the Dark Ages, and many of the works of Aristotle were forgotten and lost. Some of his texts, however, were reintroduced to Europe during the 1000s and 1100s and were translated into Latin. The Church, the dominant political and cultural force in Western Europe, at first prohibited the works of Aristotle, but soon thereafter the Church accepted them and incorporated them into Christian doctrine. Thus, the planets and stars moved in perfect circles around Earth. Since these motions were considered natural, they were not thought to be caused by forces. Violent motion, on the other hand, was imposed motion. It was the result of forces that pushed or pulled. A cart moved because it was pulled by a horse. A tug of war was won by pulling on a rope. A ship was pushed by the force of the wind. The important thing about defining violent motion was that it had an external cause. Violent motion was imparted to objects. Objects in their natural resting places could not move by themselves. They had to be pushed or pulled. It was commonly thought for nearly 2,000 years that if an object was moving against its nature, then a force of some kind was responsible. 3.1 Boulders do not move without cause. Such motion was possible only because of an outside force. If there were no force, there would be no motion, except in the vertical direction. So the proper state of objects was one of rest, unless they were being pushed or pulled, or were moving towards their natural resting place. Most thinkers before the 1500s considered it obvious that Earth must be in its natural resting place, and assumed that a force large enough to move it was unthinkable. To them, it was clear that Earth did not move. Section 3.2 Copernicus and the Moving Earth. It was in this intellectual climate that the astronomer Nicholas Copernicus, 1473 to 1543, shown in figure 3.2, formulated his theory of the moving Earth. Copernicus reasoned that the simplest way to interpret astronomical observation was to assume that Earth and other planets moved around the Sun. Nicholas Copernicus proposed that Earth moved around the Sun. Earth moved around the Sun. This idea was extremely controversial at the time. People preferred to believe that Earth was at the center of the universe. Copernicus worked on his ideas in secret to escape persecution. In the last days of his life, and at the urging of close friends, he sent his ideas to the printer. The first copy of his work, De Revolutionibus, reached him on the day of his death, May 24th, 1543. What did Copernicus state about Earth's motion? Here's another picture of Copernicus next to the one from the book. 3.3 Galileo on motion. Galileo, the foremost scientist in late Renaissance Italy, was outspoken in his support of Copernicus. As a result, he suffered a trial and house arrest. One of Galileo's great contributions to physics was demolishing the notion that a force is necessary to keep an object moving. A force is any push or pull. Friction is the name given to the force that acts between materials that touch as they move past each other. Friction is caused by the irregularities in the surface of an object that are touching. Even very smooth surfaces have microscopic irregularities that obstruct motion. If friction were absent, a moving object would need no force forever to remain in motion. Galileo Galilei, 1564 to 1642. Galileo was born in Pisa, Italy, in the same year Shakespeare was born and Michelangelo died. He studied medicine at the University of Pisa and then changed his studies to mathematics. He developed an early interest in motion and was soon at odds with others around him who held to Aristotelian ideas on falling bodies. He left Pisa to teach at the University of Padua and became an advocate of the new theory of the solar system advanced by Copernicus. Galileo was one of the first to build a telescope and was the first to direct it to the nighttime sky. He discovered mountains on the moon and the moons of Jupiter. Here's a picture of Galileo in front of the Inquisition of the church, found guilty of heresy. And here's another picture of Galileo. Galileo as an older gentleman, and then Galileo as a much older man, near the time that he went blind. He published his findings in Italian instead of in Latin, the standard scholarly language of his time. And because of the recent invention of the printing press, his ideas reached many people. He soon encountered disagreements with the Roman Catholic Church and was warned not to teach and not to adhere to Copernican views. He restrained himself publicly for nearly 15 years, thinking he had found a way to present the Copernican views without contradicting church doctrine. Galileo published his observations and conclusions. However, he was brought to trial by the Roman Catholic Church and was found guilty, and he was forced to renounce his discoveries. By then, an old man broken in health and spirit, he was sentenced to house arrest for the remainder of his life. Nevertheless, he completed his studies on motion, and his writings were smuggled from Italy and published in Holland. Galileo had damaged his eyes years earlier by looking at the sun through a telescope, which led to his blindness at age 74. He died 4 years later. Galileo argued that only when friction is present, as it usually is a force needed to keep an object moving. He tested his idea by rolling balls along plane surfaces, tilted at different angles. He noted that a ball rolling down an inclined plane speeds up, as shown in figure 3.3a. The ball is rolling partly in the direction of the pull of Earth's gravity. He also noted that a ball rolling up an inclined plane in a direction opposed by gravity slows down, as shown in figure 3.3b. What about a ball rolling at a level surface, as shown in figure 3.3c? That ball does not roll with or against gravity. Galileo found that a ball rolling on a smooth horizontal plane has almost constant velocity. Note, Galileo did all his work before the advent of the mechanical clock. He timed some of his experiments with his pulse and others with the dripping of water drops. Einstein called Galileo the father of modern physics. Figure 3.3. Galileo rolled balls along surfaces tilted at different angles. A. When the ball rolls downward, it moves with Earth's gravity and its speed increases. B. When the ball rolls upward, it moves against gravity and loses speed. C. When the ball rolls on a level plane, it does not move with or against gravity. He stated that if friction were entirely absent, a ball moving horizontally would move forever. No push or pull would be required to keep it moving once it is set in motion. Galileo's conclusion was supported by another line of reasoning. He described two inclined planes facing each other, as in figure 3.4. A ball released to roll down one plane would roll up the other to reach nearly the same height. The smoother the planes were, the more nearly equal would be the initial and final heights. He noted that the ball tended to attain the same height, even when the second plane was longer and inclined at a smaller angle than the first plane. Always the ball went farther and tended to reach the same height. What if the angle of incline of the second plane were reduced to zero so that the plane was perfectly horizontal? Let's examine this very carefully. This figure 3.4. So we have three situations, A, B, and C. Initial position, final position, and then C, where is the final position? Now, A, the ball rolling down the incline rolls up the opposite incline and reaches its initial height. Now, we're assuming that no energy is lost, no potential energy is lost to kinetic friction. But Galileo found that it depends on how smooth things were, they were almost equal. B, as the angle of upward incline is reduced, the ball rolls a greater distance before reaching the initial height. So there's a relationship here later on with potential energy that we will see in later chapters. C, if there is no friction, the ball will never stop unless it hits something or is somehow controlled by some external force. Remember, friction is an external force, but there is no friction. How far would the ball roll? He realized that only friction would keep it from rolling forever. It was not the nature of a ball to come to rest, as Aristotle had claimed. In the absence of friction, the ball would naturally keep moving. Galileo stated that this tendency of a moving body to keep moving is natural, and that every material object resists change to its state of motion. That last sentence is essentially the first law of motion, called inertia. The property of a body to resist changes to its motion is called inertia. Galileo was concerned with how things move rather than why they move. He showed that experiment, not logic, is the best test of knowledge. Galileo's findings about motion and his concept of inertia discredited Aristotle's theory of motion. The way was open for Isaac Newton, 1642 to 1727, to synthesize a new vision of the universe. Concept check. According to Galileo, when is a force needed to keep an object moving? When is a force needed to keep an object moving? A ball is rolled across a countertop and rolls slowly to a stop. How would Aristotle interpret this behavior? How would Galileo interpret it? How would you interpret this behavior? A point to ponder. Aristotle would probably say that the ball stops because it seeks its natural state of rest. Galileo would probably say that the friction between the ball and the table overcomes the ball's natural tendency to continue rolling, overcomes the ball's inertia, and brings it to a stop. Only you can answer the last question. 3.4, Newton's Law of Inertia. On Christmas Day, in the year Galileo died, Isaac Newton was born. By age 24, he had developed his famous laws of motion. They replaced the Aristotelian ideas that dominated the thinking of the best minds for most of the previous 2,000 years. This chapter covers the first of Newton's three laws of motion. Newton's two other laws of motion are covered in the following chapters. 2 and 3 will be covered in the following chapters. Newton's first law, usually called the law of inertia, is a restatement of Galileo's idea that a force is not needed to keep an object moving. Newton's first law states that every object continues in a state of rest or in a uniform, that's important, uniform speed in the straight line unless acted on by a non-zero net force. The cartoon is yours to understand. A force of gravity between the sun and its planets holds the planets in orbit around the sun. If that force of gravity suddenly disappears, what kind of path would the planets move in? It would move in a straight line at constant speed. I will demonstrate that in class. Let's look at Newton. On Christmas Day in the year 1642, the year that Galileo died, Isaac Newton was born prematurely and barely survived. Newton's birthplace was his mother's farmhouse in Woolsthorpe, England. His father died several months before his birth, and Isaac grew up under the care of his mother and his grandmother. Here's a picture of Newton in his older years. As a child, he showed no particular signs of brightness, and at age 14, he was taken out of school to work on his mother's farm. As a farmer, he was a failure, preferring to read books he borrowed from a neighboring pharmacist. An uncle sensed this scholarly potential in young Isaac and prompted him to study at the University of Cambridge, which he did for 5 years, graduating without particular distinction. A plague swept through England, and Newton retreated to his mother's farm, this time to continue his studies. At the farm, when he was 23 and 24 years old, he laid out the foundations for the science of physics. Seeing an apple fall to the ground led him to consider the force of gravity extending to the moon and beyond. He formulated the law of universal gravitation, as well as much of calculus. He invented the calculus, a very important mathematical tool in science. He extended Galileo's work and developed the three fundamental laws of motion. He also formulated a theory of the nature of light and showed, using prisms, that white light is composed of all colors of the rainbow. It was his experiments with prisms that first made him famous. You might want to look up the scientist from the Middle Ages called Alhazen, the father of optics. When the plague subsided, Newton returned to Cambridge and soon established a reputation for himself as a first-rate mathematician. His mathematics teacher resigned in his favor, and Newton was appointed the Lucasian Professor of Mathematics. He held this post for 28 years. In 1672, he was elected to the Royal Society, where he exhibited the world's first reflector telescope. It can still be seen, preserved at the Library of the Royal Society in London, with the inscription, "The first reflecting telescope invented by Sir Isaac Newton and made with his own hands." It wasn't until Newton was 42 that he began to write one of his greatest scientific books ever written, the Principia Mathematica Philosophiae Naturalis. And here's a picture of the cover of volumes 1 and 2. He wrote the work in Latin and completed it in 18 months. It appeared in print in 1687 and wasn't printed in English until 1729, 2 years after his death. When asked how he was able to make so many discoveries, Newton replied that he solved his problems by continually thinking very long and hard about them, and not by sudden insight. At the age of 46, he was elected a member of Parliament. He attended the sessions in Parliament for 2 years and never gave a speech. One day he rose, and the House fell silent to hear the great man. Newton's speech was very brief. He simply requested that a window be closed because of a draft. Although Newton's hair turned gray at 30, it remained full, long, and wavy all his life. And here is Neil deGrasse Tyson with a quote: "On this day long ago, a child was born who, by age 30, would transform the world. Happy birthday, Isaac Newton, December 25th, 1642." Unlike others of his time, he did not wear a wig. He was a modest man, although very sensitive to criticism. He never married. He remained healthy in body and mind into old age. At 80, he still had all his teeth, his eyesight and hearing were sharp, and his mind was alert. In his lifetime, he was regarded by his countrymen as the greatest scientist who ever lived. In 1705, he was knighted by Queen Anne. Newton died at age 85 and was buried in Westminster Abbey along with England's kings and heroes. Newton opened up the universe, showing that the same natural laws that act on Earth govern the larger cosmos as well. For humankind, this led to increased humility, but also to hope and inspiration because of the evidence of a rational order. Newton ushered in the age of reason. His ideas and insights truly changed the world and elevated the human condition. Objects at rest. Simply put, things tend to keep on doing what they're already doing. Dishes on a tabletop, for example, are in a state of rest. They tend to remain at rest, as is evidenced if you snap a tablecloth from beneath them, as shown in figure 3.5. Try this at first with some unbreakable dishes. If you do it properly, you'll find the brief and small forces of friction are not significant enough to appreciably move the dishes. Close inspection will show that brief friction between the dishes and the fast-moving tablecloth starts the dishes moving. But immediately after the tablecloth is removed, friction between the dishes and the table stops them. And objects at rest tend to remain at rest. Whoosh. Objects in a state of rest tend to remain at rest. Only a force will change that state. Objects in motion. Now consider an object in motion. If you slide a hockey puck along a surface of a city street, the puck quite soon comes to rest. If you slide it along ice, it slides for a longer distance. This is because the friction force is very small. If you slide it along an air table where friction is practically absent, such as the one shown in figure 3.6, it slides with no apparent loss in speed. We see that in the absence of forces, a moving object tends to move in a straight line indefinitely. Toss an object from a space station located in a vacuum of outer space, and the object will move forever. Is it correct to say that the reason an object resists change and persists in its state of motion is that it has inertia? Notice that Newton's law of inertia and the equilibrium rule of chapter 2 say the same thing. When the sum of the forces equals 0, objects don't change their states of motion. Something to consider. Now let's look at the problem. In a strict sense, no. We don't know the reason why objects persist in their motion when nothing acts on them. But we know that they do, and we call this property inertia. We understand many things, and we have labels for these things. There are also many things we do not understand, and we have labels for these things too. Education consists not so much of acquiring new labels, but in learning what is understood, what is not, and why. Blast of air from many tiny holes provides a nearly frictionless, free surface on an air table. It has some friction because of air resistance, but It greatly reduces it. It will move by virtue of its own inertia. We see that the law of inertia provides a completely different way of viewing motion. Whereas the ancients thought continual forces were needed to maintain motion, we now know that objects continue to move by themselves. Forces are needed to overcome any friction that may be present and to set objects in motion initially. Once the object is in motion in a force-free environment, it will move in a straight line indefinitely. In Chapter 6, we'll see that forces are needed to accelerate objects, but not to maintain motion if there is no friction. What is Newton's first law of motion? Chapter 6 will be Newton's second law of motion, and Chapter 7 will look at Newton's third law of motion. 3.5, mass, a measure of inertia. Kick an empty can, as shown in figure 3.7, and it moves. Kick a can filled with sand, and it doesn't move as much. Kick a can filled with steel nails, and you'll hurt your foot. The nail-filled can has more inertia than the sand-filled can, which in turn has more inertia than the empty can. The amount of inertia an object has depends on its mass, which is roughly the amount of material present in the object. The more mass an object has, the greater its inertia, and the more force it takes to change the state of motion. Mass is a measure of the inertia of an object. Mass is not volume. Do not confuse mass and volume. They are entirely different concepts. Figure 3.7. You can tell how much matter is in a can when you kick it. Although I would not kick a can unless I knew how much material was in it. Volume is a measure of space and is measured in units such as cubic centimeters, cubic meters, and liters. Mass is measured in the fundamental unit of kilograms. If an object has a large mass, it may or may not have a large volume. For example, equal-sized bags of cotton and nails may have equal volumes, but very unequal masses. How many kilograms of matter an object contains and how much space the object occupies are two different things. A liter of milk, juice, or soda, anything that is mainly water, has a mass of about 1 kilogram. Which has more mass, a feather pillow or a common automobile battery, as shown in figure 3.8? Clearly, an automobile battery is more difficult to set into motion. The pillow has larger size volume, but a smaller mass. This is evidence of the battery's greater inertia and hence its greater mass. The pillow may be bigger, that is, it may have a larger volume, but it has less mass. Mass is different from volume. Mass is not weight. Mass is often confused with weight. We say a heavy object contains a lot of matter. We often determine the amount of matter in an object by measuring its gravitational attraction to Earth. However, mass is more fundamental than weight. Mass is a measure of the amount of material in an object and depends only on the number of and kind of atoms that compose it. Weight, on the other hand, is a measure of the gravitational force acting on the object. Weight depends on an object's location. Mass is inertia. The amount of material in a particular stone is the same whether the stone is located on Earth or on the moon or in outer space. Hence, the stone's mass is the same in all of these locations. This could be demonstrated by shaking the stone back and forth in these three locations. The same force would be required to shake the stone with the same rhythm, whether the stone was on Earth, on the moon, or in a force-free region of outer space, as shown in figure 3.9. The stone's inertia, or mass, is solely a property of the stone and not its location. But the weight of the stone would be very different on Earth and on the moon, and still different in outer space. And here's a figure. It's just as difficult to shake the stone in weightless space or on Earth or on the moon or wherever. On the surface of the moon, the stone would have only 1/6 the weight it has on Earth. This is because the force of gravity on the moon is only 1/6 as strong as it is on Earth. If the stone were in a gravity-free region of space, its weight would be zero. Its mass, on the other hand, would not be zero. Mass is different from weight. We can define mass and weight as follows. Mass is the quantity of matter in an object. More specifically, mass is a measure of the inertia or laziness that an object exhibits in response to any effort made to start it, stop it, or otherwise change its state of motion. Weight is the force of gravity on an object. While mass and weight are not the same, they are proportional to each other in a given place. Does a 2-kilogram bunch of bananas have twice as much inertia as a 1-kilogram loaf of bread? Twice as much mass, twice as much volume, twice as much weight when weighed in the same location? 2 kilograms of anything has twice the inertia and twice the mass of 1 kilogram of anything else. In the same location where mass and weight are proportional, 2 kilograms of anything will weigh twice as much as 1 kilogram of anything. Except for volume, the answer to all these questions is yes. Bananas are much more dense than bread. So 2 kilograms of bananas must occupy less volume than 1 kilogram of bread. Objects with great mass have great weight. Objects with little mass have little weight. In the same location, twice the mass weighs twice as much. Mass and weight are proportional to each other, but they are not equal to each other. Remember that mass has to do with the amount of matter in the object, while weight has to do with how strongly the matter is attracted by gravity. 1 kilogram weighs 10 newtons. In the United States, it is common to describe the amount of matter in an object by its gravitational pull to Earth, that is, by its weight. In the United States, the traditional unit of weight is the pound. In most parts of the world, however, the measure of matter is commonly expressed in units of mass. The SI unit of mass is kilogram. Its symbol is kg. At Earth's surface, a 1 kilogram bag of nails has a weight of 2.2 pounds. The SI unit of force is the newton, named after guess who. 1 newton is equal to slightly less than a quarter pound, about the weight of a quarter-pound burger after it is cooked. The SI symbol for the newton is the capital N and is written with the capital letter because it is named after a person. A 1 kilogram bag of nails weighs 10 newtons in SI units, as shown in figure 3.10. Away from Earth's surface, where the force of gravity is less, the bag of nails weighs less. If you know the mass of something in kilograms and want its weight in newtons at the Earth's surface, multiply the number of kilograms by 10. It's actually 9.8, but we round it to 10. And there is figure 3.10. Figure 3.10, 1 kilogram of nails weighs 10 newtons, which is equal to 2.2 pounds. It's actually 9.8, but we say 10 because we round off for mathematical simplicity. Or if you know the weight in newtons, divide by 10, and you'll have the mass in kilograms. Once again, weight and mass are proportional to each other. Mass is a property within the body. Weight is an outside force on the body. What is the relationship between mass and inertia? Linked to space station. Pioneer and Voyager spacecraft launched in the late 1970s have gone beyond the orbits of Saturn, Uranus, and Pluto, and are still cruising beyond the solar system. Initially, force supplied by rockets sent the spacecraft on their journeys. However, once in outer space, these engines supplied no more force, except for the gravitational effect of the stars and planets in the universe. The motion of the spacecraft will continue without change. 3.6. The moving Earth again. Copernicus announced the idea of the moving Earth in the 16th century. This controversial idea stimulated much argument and debate. One of the arguments against the moving Earth was as follows. Consider a bird sitting at rest on the top of a tall tree, as shown in figure 3.11. On the ground below is a fat, juicy worm. The bird sees the worm, drops down vertically, and catches it. It was argued that this would not be possible if Earth moved as Copernicus suggested. If Copernicus were correct, Earth would have to travel at a speed of 107,000 kilometers per hour to circle the sun in 1 year. Convert the speed to kilometers per second, and you'll get 30 kilometers per second. Figure 3.11. Earth does not need to be at rest for the bird to catch the worm, because everybody is moving at the same speed. The Earth, the bird, the worm, the air, the tree. Even if the bird could descend from the branch in 1 second, the worm would have been swept away by the moving Earth for a distance of 30 kilometers. For the bird to catch the worm under the circumstance would be an impossible task. The fact that birds do catch worms from high tree branches seems to be clear evidence that Earth must be at rest. Objects move with the Earth. Can you refute this argument? You can if you invoke the idea of inertia. You see, not only is the Earth moving at 30 kilometers per second, but so are the tree, the branch of the tree, the bird that sits on it, the worm below, and even the air in between. All are moving at 30 kilometers per second. Something to consider. The law of inertia states that objects in motion remain in motion if no unbalanced forces act on them. So objects on Earth move with Earth as Earth moves around the sun. When the bird drops from the branch, its initial sideways motion of 30 kilometers per second remains unchanged. It catches the worm and is quite unaffected by the motion of its total environment. Stand next to a wall. Jump up so that your feet no longer touch the floor. Does the 30 kilometer per second wall slam into you? Why not? Because you are also traveling at 30 kilometers per second. Before, during, and after you jump, the 30 kilometers per second is the speed of Earth relative to the sun, not the speed of the wall relative to you. Objects move with vehicles. 400 years ago, people had difficulty with the idea like these, not only because they failed to acknowledge the concept of inertia, but also because they are not accustomed to moving in high-speed vehicles. Slow, bumpy rides in horse-drawn carriages do not lend themselves to experiments that reveal inertia. Today, as shown in figure 3.12, we flip a coin in a high-speed car, bus, or plane and catch the vertically moving coin as we would if the vehicle were at rest. We see evidence for the law of inertia when the horizontal motion of the coin before, during, and after the catch is the same. The coin keeps up with us. The vertical force of gravity affects only the vertical motion of the coin. Our notions of motion today are very different from those of our distant ancestors. Aristotle did not recognize the idea of inertia because he did not see that all moving things follow the same rules. Figure 3.12, flip a coin in a high-speed airplane and it behaves as if the plane were at rest. The coin keeps up with you, inertia in action. He imagined different rules for motion in the heavens and motion on Earth. He saw horizontal motion as unnatural, requiring a sustained force. Notes: inertia safety. The more than 3 million kilogram steel ball hanging at the 87th floor of the tallest skyscraper in Taipei helps stabilize the 101-story building against vibration caused by earthquakes or strong winds. Galileo and Newton, on the other hand, saw that all moving things follow the same rules. To them, moving things required no force to keep moving if friction was not present. We can only wonder how differently science might have progressed if Aristotle had recognized the unity of all kinds of motion and friction's effect on motion. How can the law of inertia apply to objects in motion? The summary: Aristotle, the foremost Greek scientist, studied motion and divided it into two types: natural motion and violent motion. Copernicus reasoned that the simplest way to interpret astronomical observation was to assume that Earth and other planets move around the sun. Galileo argued that only when friction is present, as it usually is a force needed to keep an object moving. Newton's first law states that every object continues in a state of rest or of uniform speed in a straight line, unless acted on by a non-zero net force. The more mass an object has, the greater its inertia, and the more force it takes to change its state of motion. The law of inertia states that objects in motion remain in motion if no unbalanced forces act on them.